Yeah, thanks for everyone for joining. I wanted to have like this internal presentation about the entire like NPoS and election subsystem, how it's working right now, and some of the changes that will be coming. And this is mostly to like empower other people to understand it, help me with it, and maybe more important than anything else, help me with reviewing like the upcoming code that's coming. I have about like 30, 40-ish slides, so I expect like maybe it would take an hour or so if I go through all of them in one go, or maybe less. But feel free to like interrupt me at any point. I really don't want to like just go through them, and I think in that case it should also be it might be a little bit boring. So feel free to ask questions at any point if you want. Can someone just confirm that you're still hearing me and that everything is you're also seeing the slides?
Yep, loud and clear.
We're good.
Okay. Yeah, let's begin with the definition of like what is this election that we're talking about in a very generic term. I'll just put like a few formula or keywords here just to get a little bit familiar with the terminology. What we refer to as election is a function of a set of voters and a set of targets, which gives us at the end of the day a set of winners that we then use in some ways. Which is like, I guess, the generic definition that you would also expect from an election. So you have some people who vote, there are some candidates which we refer to as targets, and some of those candidates will be elected as winners. We care about the winners and who ended up backing which winner as well. We get to more details of this. The voter term itself can be broken down into something like a tuple of account ID, which is the voter itself, some weight that's associated with this vote. So if this is like a nominator, this would be like their locked stake. If this is in governance, again, it would be different locked stake. But yeah, it could have different meanings, but generically we call it vote weight. And it's some numeric value. And a vector, or in the more modern idiom, bounded vector of account IDs that are the targets that this voter has voted for. And as mentioned, vote weight itself is also just a numeric value most often, or in the current code base, always use 64. One important keyword that's also important is that to the voters and targets together, we refer to them as a snapshot, because they're the entire state or the snapshot that you need to compute to run this function, basically. Like, yeah, it's just another piece of terminology. So we can simplify the previous function notation as like a function that takes a snapshot and spits out some winners and who's backing them. And let's also break down this term winners a little bit further. So each winner is specified by amount of support that it's receiving. So a total amount of support and a number of individuals who are backing them. So let's say if I'm a validator and 5 nominators are actually backing me or supporting me, and each of them are backing me by 10 units of vote weight, my total support would be 50, and I would have a nested, like these voters in inner vector would refer to those 5 nominators, each of their account IDs and the amount that they're backing me. So yeah, the winners thing actually translates to a vector of like the winner itself and the amount of support that it's receiving. This is also what we call the winners. And yeah, so the last version would look like something like this. You get a bunch of voters or targets, or AKA snapshot, and you receive and you spit out a output that we call supports. So like a vec of supports, a vec of account IDs and supports.
Okay, so the U128 is the vote weight, right? And voters vec.
I actually noticed this myself while I was talking. I guess it's a bit strange at this point that this is U128, this is U64. You can like it's not for reasons that I will get into, or maybe I won't in this talk. But I also noticed it myself that yeah, these two could in principle be the same thing.
Okay. Well, the most important thing is like if we take the aggregate of all the U128s in the voters vector and add them together, you get the total, right?
Yes, exactly. So this total, you can even actually not store it. You can I mean, we do store it, but you can in principle not store it and just sum up all of these guys individually whenever you want to access it.
That's gonna take a while because
correct.
we have a lot of validators and nominators.
Yeah. Some validators have lots of nominators.
Mhm.
So yeah, let's look at like an example. We have like a bunch of voters on this side. These slides, by the way, as you see, are like 100% raw. So I apologize if they're not very eloquent. I tried to just make them in minimal time possible. You have a bunch of voters, a bunch of targets on one side. The first, let's say, complementary input is that each of these voters have a vote weight, which is 10 in this case. Not very interesting, but for all of them, for the sake of simplicity, 10. And all of them just name a bunch of like, I vote for that guy, I vote for Bob, I vote for, like, a lot of edges that exist in this graph of voters to targets. And the next step of like when we get closer to that support section and the outcome of the election is that we need to specify, or an election algorithm would need to specify, well, first of all, which of these targets should be winner, like should end up being a winner, who is backing them, and who is backing them, and also among those who are backing them. So in this case, like you can see, 1 ended up backing 2 of the winners, 3 is backing 2, 4 is backing 2, 5 is backing only 1 of them. And more importantly, among those who are backing them, how their stake should be distributed. So all of these guys had like 10 units of vote weight. Well, for 5, it's kind of simple because 5 is only backing 1 person. But 4, 3, and 1, you need to somehow conclude how you want to distribute their stake between these edges that are basically active. So in this case, I kind of highlighted them, and I chose them completely arbitrary, like with no thought behind it. But a well thought out election algorithm would actually think about this and try and optimize a certain function or certain criteria based on it. In this case, this one is equal, this one is not equal, this one is highly skewed, and this one is very trivial. Also, what we get on the other side is that each of these winners would then, once the weight of these edges is determined, each of these winners would get a final backing amount, or this is basically this is specifically this thing, like support total, like their total amount of support, which in this case is 31 for this guy and 9 for this guy. Yeah, and this is like just one, let's say, very simple example of how what an election algorithm should do. Actually, like it really all boils down to determining the weights of these edges, let's say, because once you know that, everything else can be deduced from that. So now let's talk about election score. Like, let's say we have this, or like I propose this result, this outcome for a election, and how do we evaluate it? And this is like basically part of like the Polkadot. Yeah, and this is like a little bit Polkadot specific at the moment, and it's, let's say, part of the protocol that we optimize for certain criteria that I will get into, but in principle, it can be anything. The score criteria that we have at the moment is that we want the minimum backing stake among all the elected ones to be maximized. Yes, and I realize this is wrong. We want the sum of backing stake, again, among the winners to also be maximized. So ignore this emoji, this is wrong. And we want the variance of the backing stake among the winners to be minimized. So this basically like the score of this election that I kind of just made up here is 9, because this guy is the minimum between these two and is 9, has 9 units backing it. The sum of stake is 40, which kind of makes sense because 4 nominators are active and each of them had 10 units of weight to begin with. And the variance we represented with like the sum squared, and we want this to be minimized. Basically, this is saying that we want these two winners, or the set of winners. I mean, this is like 2, but in reality, we have multiple hundreds. We want them to be as close together as possible. Yeah, and as I said, like implementation-wise, this is kind of like at the moment hard-coded very deep into the code that this is the definition of score, and how it should be, but in reality, it's actually kind of tailored toward Polkadot's need. It is what Polkadot wants to optimize for, but it's quite easy to refactor it in such a way that there you could have other criteria. Yeah, and a few observations out of this election scoring mechanism. One is that the final score is only a function of the final backing of each validator. So if you look at this graph, as long as B and C receive the same amount of backing, it doesn't really matter how these edges are distributed. So in practice, we can actually go and, let's say, trim these edges in a way that these two numbers, like 31 and 9, like the final backings that we care about in score, don't change, which is actually possible with numerous algorithms, or at least one that we use. And we don't change the score. Yeah, so this is actually something that's like an algorithm that we refer to the code as like reducing a solution. Basically, we compute the outcome with like the full graph, then we kind of freeze this side of it. Like we're not going to tweak any winner's final backing stake. And then we start cutting off edges so that we get a smaller graph of solution. And the other, I mean, this is not really an observation, but the fact is that I will explain this further in upcoming slides, but the chain really cares only about the score of a solution. Like and we accept solutions from, we accept these graphs, I'm referring to them as solutions, but yeah, the name is solution, from different sources, or they can come from different means or protocols, but the score is the one and only criteria of its worth, let's say, or if we want to evaluate them. So yeah, now also let's talk about how we represent this graph in a compact way. And the reason that we want that is that, as I kind of hinted to in the previous slide, but again, I need to get into in the future, we definitely want to send these solutions around as transactions, or generally speaking on the wire, and so we want them to be small. We also want them to fit into blocks at times. Again, another criteria. If you have a big graph, it's surprisingly easy to hit that 5 megabytes block without any optimization. And when you think about that winner's graph, again, I'm going to just quickly to remind you of it. So we want to encode basically these bold edges, including the nominators and including the voters and the targets that are winner. You basically have two ways of doing it. You either do it in voter major or target major. Voter major basically means you name all the voters and the targets that they are backing and how much they back him, or target major, the other way around. You name the targets and how much backing they are receiving. Basically, target major is what I referred to earlier as supports, or that data struct supports. And voter major, I think I called it here. No, I haven't actually showed it yet. So yeah, we'll get to it next. And for reasons we actually prefer the first one, voter major. One of them being that we have, so I think the more important one is actually that we store nominators, like we store nominators in a way that is much easier to check a solution if it's voter major. It's a little bit detailed, but just accept it as a fact from me. And the other reason being that, yeah, if it's target major, you're always repeating more nominators, right? Because if it's target major, you name each target once, and then the nominators are repeated multiple times, because each voter could vote different targets, and nominators will take more space in this case. Yeah, and I realized while I was writing this slide that it's a good time to rethink all of this as well. But again, it's something beyond the scope of this presentation. So now let's look at the voter major representation of an election result. So we're already familiar with this support thingy. We name the winner, like B is a winner, and it's receiving this much backing from these people, which, thanks to my very creative color highlighting should be rather clear now. And the other way, the naming is kind of trivial. It's just like the historical names I came up with, but the voter major variant, we call it election result. Yeah, not very, yeah. If I would rewrite this right now, I would name them differently, but again, it's too late, or not story for another day. And it's totally it's exactly the other way around. You say there exists a voter with ID 1 and it's backing B and C with these amounts. There exists a voter 3 and it's backing B and C with these amounts, etc., etc. Now let's look at this election result and how we can make it small. So this is like a simplified version of the same election result. I just made it a bit smaller. So with all this like color highlighting and stuff, it becomes a bit easier. You can see the nominator, the voter, aka nominator, is like this color. This bluish color is the targets, and the greens are the vote weights, basically. First observation that all of each of these voters and targets is, if it wants to be an account ID, it's 32 bytes. It's quite big, not very good. And what we do is we replace them with an index, with a numeric index. And I will get into where the source of truth for that index is. So let's say there exists a nominator called Alice with an account ID, some account ID. And now it needs to replace with index 10. Where does that 10 come from? Where is the source of truth to then map 10 again back to Alice? I'll get to it. But for now, we can just assume that we can actually map voters and targets to numeric indices. And then thanks to the scale codex compact encoding, it can become fairly small. So if you have a few hundred validators in total and you want to elect 100 of them, this won't take more than like a few bytes whenever you want to encode a validator, as opposed to 32 bytes fixed for everyone. Yeah, I can also hint at already tell how these indices are basically computed. At some point in time, we want to go and create that snapshot that I talked about, which constitutes grabbing all the validators, nominators, aka targets or voters, from their associated maps in storage, and then putting them in a flat vector or bounded vector so that they can be indexed by a number. Like, this serves two functions. It makes them be indexable, if that's the word, or indexable, I don't know, like capable of being indexed by a number. And it also brings a few other values to this entire system. Yeah, most notably that if you have a snapshot, the staking system doesn't need to like freeze itself during the election. Like, people can still bond and unbond and do whatever they want, but the system has a snapshot that doesn't change. Anyway, account IDs get converted to numerical values. And I guess these are like reasonable values. Like for targets, you use U16, for voters, you use U32, or U16 for both of them. No, okay, now U16 is 65,000 limit. So it depends on how big the network is, right? Like you can decide. Next thing is that numerical value, like the vote weight, can be also like 4, 8, or some number of bytes in that order. And we can also reduce that into a ratio, like per thing, per X, per bill, percent. We have these numerical types in SP arithmetic in substrate primitives. And this has two benefits. One is that these per things are usually smaller. Like if you use a per U16 is perfectly good enough. I mean, there's some accuracy loss when you convert a number into a percent, but it's good enough. Like, we don't care about the, whatever is less than total issuance, for example. Or like we have to remember that, for example, for most chains, including Polkadot, 1 dot is 10 to the power of 10. So a loss of few thousand units of currency is actually completely insignificant. A few million units of currency, or a few million planks, as they're called in the Polkadot paper, is also pretty insignificant. So anyway, instead of having like, let's say 5 and 5, we replace these 5s with a percent, like 50% and 50%. And then the second benefit of this is that we can remove the second one, because if you already know this is 50%, the second one is clearly 50%. Or if you're voting for, if you are backing only one target, You don't even need to mention that numerical value. It's your entire vote weight. It's your entire stake. Yeah, and lastly, what we do is we group the voters by the number of people that they're backing. And this allows us to use a fixed size array instead of using a vector, because the vector needs to encode its own length. I mean, this is like a very tiny optimization, and it's making the code really difficult. Again, going back in time, I think I wouldn't have done this, but kind of too late. So the final structure of this thing that I kind of formulated right now that I can call compact election result is something like this. You have like a struct which has some fields, and a field for voters who vote for only one person. And that's like a vector of just a tuple of a voter index and target index. No need to mention what ratio, what vote weight, it's all known. It's 100%, it's the entire stake. For those who vote for one person, it's like a one voter index, one target, like a fixed size array of size 1, which is a pair of target and a ratio. And the last one, which we don't name anymore, because the last one is whatever is left from the previous percentages, if that makes sense. As like one example, if there's someone's backing 3, so one voter is backing 3 targets, and the ratio for those is 30% and 40%. The last one is known to be 30%. Yeah, and this is also generated by a macro, this struct, which again I think can be refactored in some easier ways. Again, yeah, this part I think it's working. I'm not going to touch it now, but could be redone later. Okay, I'm going to walk over this as well, and then I'm going to actually ask for like if anyone has some thoughts so far or questions. Lastly, I've mentioned multiple times that we're getting there. I'm getting to the point where I'll explain exactly how, but we want to accept solutions in this compact form from untrusted sources, which is also why we want them to be sent over wire or included in the block, etc., etc. And what do we check to check if they're correct on chain? Because we can't trust anything that comes in, right? I mean, that can be wrong. It can be a lie. It can be false. We check that all edges must be correct. So if someone is claiming to back someone, they must actually nominate them. And in this case, the source of truth is pallet staking, of course. So all edges must be correct. In some ways, because we also break down the vote weights to ratios, it's kind of makes that part easier. We don't really need to check the stake of anyone because yeah, the stakes are all percentages. Like if one voter is claiming to have backed 3 winners in this compact election result, we only check that they actually nominated them. But the ratios, I mean, it's just some percentages, and whatever is their stake is multiplied by it. So next thing is that quite often we want these untrusted solutions to claim a score in advance. So we receive a solution, we don't want to go over it and check everything and compute its score, the score that I explained earlier, what the definition for is. We don't want it to we don't want to do that on the fly. We want it to claim a score, and we assume it's correct. At the very end, we check if it's actually correct. So there will come a time where we actually want to check the score of a solution as well, which we talked about, and I kind of explained how it's computed. You can also now imagine the score is very easy to compute once you convert this like compact thingy into a target major data struct, like because the score is only a function of the final stake of the winners. Yeah, some notes. One detail that might actually change in the near future is that we also currently strictly check that the solution also represents the enough or correct number of winners. So when staking wants an election to happen that gives it 300 winners, aka 300 validators, it must eventually give 300 validators, no more or no less. We probably will relax this in the near future, so it will be more like less is also acceptable. And no need to do anything else about it, because a solution that has less winners inevitably has a lower score, because the second element of the score was total amounts at stake. And if you have less winners, that number is probably less. Okay, this was all like some background knowledge. I'm gonna like use just drink something. My throat is a bit itchy. Now is a good time to ask questions if anyone has any. If not, I'll continue.
I would like to ask something just to make sure that I have understood it properly.
Yeah.
The compact, the last struct that you have shown, the compact thing, that is grouped like by the number of nominations.
So this is grouped by the yes, the number of nominations.
Nomination, accounts with one nomination, accounts with two nominations, and like,
correct.
Okay.
Correct.
Thank
you. Just to be more specific, accounts with, but not really nomination, because you can vote for 24 people, but only one of them is active. This is grouped by number of active nominations. So if in the election result you ended up backing 3 people, you end up in this field of this struct. But as I said, this is like a very tiny micro optimization. I mean, it's saving some bytes in the size, but at the moment we are quite far from this length bottleneck. Actually, our problems are elsewhere. I guess, but yeah, I could, I can't go back in time and change this. So yeah, let's talk a little bit.
Yeah, if I recall correctly, there's only ever in the normal case, there's only ever going to be one active nomination. Is that correct?
That's a very good point, a very good question. That's only because of this reduce algorithm. No, there are people who have more, but this reduce algorithm is quite often so good that it manages to remove everyone's edges except one and keep the score constant. Does that make sense?
Removes everyone's edges and keep the score constant. Is that what you said?
Yes. So once I didn't include this in this slide, but I have it somewhere else. But yeah, it's probably, it's too much. Like, I don't know where it is to find it right now. So yeah, the reason that we have this behavior in Polkadot and Kusama right now is only because the tools and the binaries that are right now submitting these solutions to the chain, which I will explain next, are by default running this reduce algorithm. And if they don't run it, then it's actually worse UX for everyone, because imagine you're backing 16 people and then you receive 16 different tiny reward transactions. There's going to be a lot more people oversubscribed. Let me also talk briefly about this oversubscription. So every validator can have only, I think, 512 rewardable nominators, and if we don't reduce, this number is going to blow up. But yeah, again, to recap, the reason that we have this observation now, or this situation, which is actually a good thing, is that all entities that are computing these election results and solutions right now run the reduce algorithm. So even if you vote for 16 people, you end up backing one of them. But the result of the solution is, but the result of the election is same as if you have backed all 16 of them. Does that make sense?
In other words, the support struct or whatever the result is will always contain sort of like all of these, all the nominations that you've made.
No, by the time we reach that stage, they're already trimmed. Let me just recap again. I think this will help, but this is an important point. Some entity off chain computes this election result and wants to submit it to the chain. And this election result has a particular score, let's say whatever, 100, 100 score. it can submit it as it is to the chain, in which case you as a nominator would, if you have voted for 8 people and all of them are actually elected and winner, your stake is somehow distributed between them. So you're like 10% this, 10% that, 20% this, 10% that. But these entities that run the election and then submit it run this reduce algorithm so that all of these edges that you have as one nominator get reduced to 1, 2, or maximum 3 in most cases, but the score of the entire solution doesn't change.
Oh, so in that case, it's the backing that has changed, the per thing.
So you want to know what changes, right? So what I would say is that I think it's best to describe it here. The score, and most notably these numbers like 31 and 9, do not change, cannot change, because they are affecting the score, and we don't want the score to be changed, or more importantly, we don't want the score to be lessened, like reduced. But these edges do change. So if, for example, let me see if I can find an example here. So let's say, yeah, I mean, let's say, imagine somehow there's an algorithm that can come and look at these 7 edges. I mean, I have 7 active edges here, and reduce them to 4, but such that these 2 numbers, 31 and 9, do not change. We want that because it makes the whole thing smaller, but in effect, it's the same thing from the perspective of a selection score or quality.
I'm just wondering how that would make sense, because that would mean that you would lose nominators that way, because you're removing edges, right?
Edges. I mean, no one gets removed to no edge, because that doesn't make sense. The algorithm does not do that. I mean, if it were to do that, that would be a mistake, because then you're removing a nominator. If you remove the nominator, you are inevitably reducing the sum of amounts at stake. You are making the score less. This whole assumption chain breaks. No, you are only removing edges. So let's say like these 2 guys, they are now voting for 2 people. Let's say somehow we make, and they are voting for the same pair, right? So 7, yeah, they're both voting for B and C. 3 and 4 are both voting for B and C. I think in this case it won't hold, but if we were to make them 3 only backs B and 4 only backs C, we make such tweaks, you know? So some edges are removed, but nominators stay the same. And more importantly, the winners and their total backing also stays the same. Did I succeed in explaining it better this time, or?
If one nominator only ever votes for one,
then it won't get reduced. Then it won't get reduced.
Yeah, but in this case, like say for example 3 or 4, you and you're trying to reduce it so that they're only.
I lost your connection. Can you repeat? I lost your voice for a sec. Can you repeat?
If say 3 or 4, 3 or 4 all are voting for 2 validators, and you have this algorithm that tries to make it so that they only ever vote for 1. Is that correct?
Yes. They only ever vote for 1. Yeah, I mean, that's like a tricky way to put it. I would rephrase it as remove edges when possible. Just that, you know?
Okay.
So let's say now, actually, I think in this case, we almost certainly can do it, right? Because let's say if we, so how much is this? This guy is receiving 7 and 9. No, okay, no, we can't do it in this case. Yeah, but yeah, no, we can't. Or I don't have an example. I don't have the process of how this algorithm works in my head so good, like that well, to be able to check if it's applicable here. But it seemed like it is. But again, just we remove some of these edges such that the score does not change, such that the winners don't really change. The nominators also don't change, only their votes might be less than what it actually really was. So you nominate 16, you end up backing 2 of them, something like that.
Okay, I can convince myself how it works. Like, let's say, for example, you have one that votes for A. You could definitely remove that edge because A isn't active.
That doesn't even come into the game. Okay, let's just do it. Where do I have to go to find this in sheet? No, docs.google. Because I have an example of it somewhere. Yeah, okay, it's this one. This is an old presentation. Yeah, you can see some similarities between it, and it was a very long presentation. Not a good one. It was too technical. I mean, no, we come back. Yeah, we're almost there. Okay, I think it's this slide. So yeah, here we have a similar example. We have like these nominators whose stake is split it like 50%, 50%. This one is simple because it's 100%, and then these validators end up having some amount of stake because like this is a better example. It's more realistic. And then yeah, when you convert these percentages to values, it ends up looking like this. This reduce algorithm works based on this premises. As long as there's a cycle in this graph, one edge can definitely be removed. So we spot the cycle, remove it, then scan it for a cycle again, something like this. Yeah, so now this is the same graph as here. I just unmangled it, or whatever the word is. So I moved stuff around so you can clearly see that there is a cycle here. Yeah, let's just see how it works. I think the way it works, you would find the smallest edge in the cycle. So in this cycle, this edge is 7.5, this edge is 10, this edge is 10, this edge is 15, this edge is 15, this edge is 7.5. So one of these two can definitely be removed. You spot the minimum and you assume that one's 0. So now if this one, now the thing is, this winner, this validator, is receiving 7.5 units less of stake. So we need to compensate it by tweaking this guy, which is what we do next. Okay, no, I did it the other way. So let's look at it from the other way around. We get to that as well. So if this edge is removed, this edge needs to be 50. So then this validator is receiving 7.5 extra units from this side. So this needs to be removed by 7.5. And you continue this cycle all the way, and you end up, here I had a good numerical example where you can see that the backing of each validator stayed constant in this process all the way. And we basically removed this edge, this vote. Like these 3 validators are still elected. They have the same backing, but we managed to remove one edge, and we just repeat this as long as we can.
Wouldn't that then change the vote for a nominator, because you just removed an edge? That means that that this particular nominator has voted one less validator.
Correct. It will.
It's not about they have voted. It's the fact that like when the nominators you pick, we don't let you rank them. You just say these are all people who I think would be valid, right? So what Kian's method is doing here is saying that instead of you backing 2, you're going to back 1 of them, and within the rules of how you pick the nominators, that's allowable.
Yes.
So like technically, if you prefer, like, oh, it would be better that I had my stake, split between 2 guys this last round, that's like one opinion. But the fact is that we optimize this and we say that anyone you picked should have been good. So it didn't matter that we put you behind 1 instead of putting you behind 2, right?
Yeah. Okay, so you're describing to me how this reduced algorithm works.
Sorry, go again.
you're describing to me that how the reduced algorithm works.
Yes, yes. This
reduced-
slide was exactly how the reduced algorithm works.
Okay,
In,
so that makes it end up so that most of the time you're going to be voting for one and only one validator most of the time.
exactly.
Instead of
1, 2, or 3. I
heuristic.
mean, there are. Yeah, but I think the point here to make is like there are a few points here too. First, this is not enforced. This is only because the current, again, entities that submit these solutions, which I will get to later, and you have to use this opaque word, current entities that submit, like it's in the next slide. But yeah, currently the default submitters of solutions are opinionated and they prefer running reduce, but it's anyone who wishes otherwise can not do it and then compete, let's say. I will also explain this competition a little bit later. The other point I want to make is that, yeah, I kind of forgot the other one. Yeah, this is not enforced. This is nowhere enforced in this whole protocol though. It's just an optimization for like the future, but it already helps a lot. I think if now I think the size of like these submissions in Polkadot and Kusama are somewhere around like 50 to 100 kilobytes. If we wouldn't reduce, there would be like 1-2 megabytes. So I mean, there's clearly a point, and we would have, as I said, a shit ton of oversubscribed validators if we wouldn't do this. And the other point I wanted to make is that the narrative that I've been asked, and I tell community members directly, or there are other people from Parity who are in touch with the community, is that if you really want to split your stake in a specific way, then you should vote only for one person. So you decide how your stake is distributed. If you let our algorithm or Polkadot's algorithm do it for you, then this is how it's done. Okay. I will continue, assuming that there are nothing else. But yeah, thank you for your question. It was helpful. So yeah, now let's go a little bit, come closer to the code and the abstractions that we have. The current abstractions of the election, I mean, after multiple iterations and like 2+ years of like starting from one function in one file, is that we have like, in a very broad sense, this abstraction handling everything. You have one entity, in some case a palette, in some cases struct, being the election provider, who can answer a call to a function called elect, and then return a bunch of supports, as we discussed the terminology earlier. And then whoever calls this, we call it election consumer, but I mean, that's not really an important role. And more importantly, we have some other entity who's the election data provider. You can probably guess it's staking, or in reality, both of these are staking actually. The election data provider can respond to a function or a call to, hey, give me the voters that I need to work with. Hey, give me the targets that I need to work with. And in some cases, tell me when you probably need the next election. This is actually a mistake in the API design. Like some places, I totally assume that election data provider and election consumer are the same things. In some places, I totally have forgotten about it. I think for the sake of simplicity, we can just assume that they are one thing. And from now on, we also assume that they're one thing. So you have the election data provider, which is both the consumer of the election, the one who's going to call elect, and the one who's going to know the input of the election. Yeah, so, and this abstraction kind of like, it's the more general one, because we have, like, you can see the elect function has no input. You don't tell it, hey, here's the input, now elect for me. You assume that the election can be basically asynchronous. So what I described as election provider is actually async election provider in some way. And quite recently, I actually added a subtrait, or I made this a super trait of another one called instant election provider, where we only assume that election happens right now. But again, going back to the general abstraction, we assume asynchronity here, like the fact that election happens, election data needs to be known way ahead of time when the call to this elect function happened. So the timeline is something like this: election provider election provider asks for the election data at some point in time, so kind of like here, and you do your best to have a supports or the election result already queued and ready for when the call to elect comes. And when the call to elect comes, saying, hey, now give me my election result, this is already ready and you don't actually need to do anything. So yeah, this is a general abstraction of like how election works in Substrate. A little bit closer to the code. Now let's look at the crates that empower this and allow us to do this one by one. This is the overall hierarchy right now. And let's just start one by one. So in the primitives, we have SP NPoS elections. This is where all the raw algorithms exist. Like there's no notion of runtime, validator, nominator. This is why I'm confusing myself and everyone in the call with like using voter and nominator and then target and validator. Again, maybe going back in time wasn't worth it, but I tried to be pedantic and not use runtime or let's say blockchain or Polkadot specific terms in code that's not meant to be used only for Polkadot. So voter is basically a synonym for nominator. Target is basically a validator. We have about all these algorithms that I kind of talked about briefly in this crate implemented. So these three are the ones that basically compute an election. We have the reduce algorithm, and we have that notorious macro that implements that compact solution type. And I put this thumbs down here also to remind myself, this is again a big mistake, in my opinion, now looking back at it. Like this macro should live inside of frame because this macro is frame dependent and it makes its code again a lot easier if it were to have access to something as simple as weight type or some other frame primitives. Anyway, for now, this is where all the completely generic algorithms live. Then we have frame election provider support. So this is like a attempt to be like, I mean, it could have been a sub module or sub crate of the frame support crate, but I decided for it to be a totally different crate, to not pollute the original frame support, which is already a little bit bloated. So it's basically the equivalent of frame support, but for election stuff. This is where we have all of these glue traits that I talked about defined. So we have the election provider trait, election data provider. This one, ignore for now. I will get into it later. We have a handy trait called NPoS solver where it can be implemented for any struct that is one of these algorithms. So by the way, one of the most famous one is called fragment, which is the term that's used quite a lot. Or if you hear fragment, it's synonym to the whole election stuff. Like when someone wants to say election is broken, they just say fragment is broken. It's like kind of like a wild kind of like a catch-all phrase, let's say. Anyway, we have some handy traits to implement them for different solvers. I mean, it can be a custom solver as well, and then the rest of the code can be generic on it, kind of nice. We also have one struct here that implements election provider called on-chain sequential fragment. And this one is the one that actually does it on the fly right now, which learning from the history, you should probably not use in production, but it's very useful for testing, testnet, or fallbacks. Yeah, this one also implements the instant election provider because it is instantaneous. It's not asynchronous, actually. Then we have palette election provider multiphase. Again, going back in time, I would have just named it anything else that was shorter because who knows how many times I had to type this thing all around the code, or other people had to. It's kind of a long name, but it's a palette that provides election in multiple phases, or by relying on multiple phases where each phase can do something, let's say. So at the end of the day, it's an implementation of election provider for its outer palette. And this is where now I can go into detail about those entities that submit stuff. We basically have two entry points for accepting these compact election results. One of them is a signed phase where any signed account can reserve some deposit and in return put some solution on chain that is later on checked, and if it's correct they will get rewarded, if it's bad they get slashed. The more or less typical blockchain paradigm where you have create some incentives. And then you have the unsigned phase where validators submit a unsigned transaction. So validators, to be more specific, validators use their off-chain worker threads to compute a solution and then submit it back to the chain as a unsigned transaction. This unsigned transaction is basically an inherent, which means a data that the validator directly puts into the block, and then it's checked as well. And it kind of acts as like a fallback. So if the signed phase doesn't work, or if there are no accounts interested in submitting anything, then the validators do stuff. And it's basically a competition between these two. So we have, in some cases, a signed phase. Like in some cases, the signed phase wins. In some cases, the unsigned does. Nowadays, usually the signed phase is working well. Like we have actually a entity, like another little tool on the side called the staking miner that every day or multiple times a day is working, and it's submitting the stuff. When it's broken, the unsigned stuff is still working well as backup. There's also a little bit more detail into this palette, which I don't want to get into too much detail of it. There's another phase called emergency. So if both of them fail, then nothing happens. Basically, the palette shrugs its shoulder and say, hey, I failed. Now governance comes and rescues me, basically. But yeah, this palette is completely asynchronous as well. So it highly depends on that earlier function called predict next election, because it kind of needs to know when to expect to be ready. Now let's look at this in a bit more graphical way, and so go into more details of everything that I just explained. So at the beginning of the signed phase, a snapshot is created, like pallet staking is hauled into it, and it gives you the voters and targets, and there's some stored somewhere in this palette. During the first signed phase, any account can submit some stuff, and here I demonstrated that with like this queue, which is, as you can also see, sorted by the score of the submission. So let's say Eve, who was malicious, submitted something with a claim score of 100, but it was wrong, like it turned out to be bad. At some point it was verified and turned out to be bad. Bob submitted something correct, 95, and these two accounts also submitted something. You can also see a hint at this Parity staking miner. So one of these entities that usually submits the solution is Parity staking miner, but in principle can be anyone or anything. Any of you actually as well. I mean, there is reward to be earned here as well. Not much, but it is some money. So at the end of the sign phase, we go into this queue and start verifying them from the most potentially valuable to the least. And in this case, Eve gets slashed because her solution was bad. Bob's solution, the green one, gets queued because it was good, actually. And these two solutions, we don't really care about them. We discard them. And we don't really punish the submitters either, because they didn't do anything bad. But Eve definitely did something bad. She wasted a lot of time in this case. Then comes the unsigned phase, which, okay, I thought there was like a demonstration of the unsigned phase as well. I think it's in a further slide. Yeah, okay, doesn't matter. Then comes the unsigned phase, when the validators try and compete with this potentially queued solution via their off-chain workers. But this is, it should be only considered a backup because it's also executed in WebAssembly. It's constrained. It cannot be updated, like updating the code of the off-chain worker is currently not possible. So you can only update it when there's a new runtime upgrade, which happens not that frequent or not super frequent. And then finally, at some point in time, a call comes to this elect function, at which point we don't do anything other than just returning whatever has been queued. And if we don't have anything queued, we go into the further emergency scenarios. And whatever is queued is passed on to staking to then do stuff with. Yeah, and this was like a more detailed explanation of this pallet election provider multiphase. I really should rename it at some point. Finally, we have pallet staking, which is an implementation of the election data provider. Also acts as the election consumer, but you can pretty much forget about that abstraction anyway. And the only detail of it that I want to go into in more detail is that being the election data provider is not 100% trivial, because there could be times where you basically, just to not go into too much detail and summarize it, you want to be able to have your nominators in a sorted way. So if you have 100,000 nominators, but the election provider only asks for 20,000, you can give them the good 20,000 nominators. And this is the main challenge of staking, which we kind of started solving with help of multiple other devs. Some of them no longer with us, actually, mid last year, and now it's actually, with the next release, it will be fully functioning in Polkadot. And this is where this pallet bags list comes into play. It's part of the election pallet group, but it's quite a generic pallet that is capable of keeping some data in a semi-sorted way. So let's look at how it works. And again, in a very simplified word, pallet staking only contains this flat map of nominators where A, B, C, D have some amount of stake, 10, 25, 22. And this bags list pallet is like a duplication of this data that's stored somewhere else, but it's then sorted into groups, or as we call them, bags. Yeah. Good, I don't know, maybe not the best name, but yeah, there are different bags for different ranges of stake, basically. So you can see then 5 and 10 are grouped together, 20 and 22 are grouped together. And then once we want to iterate or then get the best voters, we can use these bags, and we can start from the highest value bag and then go to the lowest value bag. So basically these bags are like a linked list, but within them there is no order. Or let's just say within them, the ordering is not enforced. Users themselves can claim that, hey, I have a better order, I have more stake than that guy, I should go in front of him. It's an operation that we call rebagging, or no, this is actually change within a bag. There could be also a scenario where you can send a transaction and say, hey, I'm in the wrong bag, please send me to the correct one. But yeah, this is like, this palette keeps a semi-sorted list, basically. And in the current implementation, the staking palette would automatically update the bags whenever there's a transaction. So whenever there's like a bond extra on bond, do we have anything else? I don't know, any other transaction that alters the bond of accounts, it's automatically reflected in the bags list, but slashing and reward is not. And we expect the users to or nominators to care enough to do that themselves. So there are these permissionless transactions that I explained that users can go and themselves say, hey, I used to be in this bag. So let's say in this case, A, which already had 10 units of stake, now earn some staking reward, is now 25. A itself should and can go and send a transaction and say, hey, now I belong to this bag, and then it gets moved to that bag. So yeah, and this solves a huge pain point, which is that we don't really then need to keep the number of nominators bounded in the staking palette anymore, because now we have a way to fetch the top whatever we want to support for election. Because of course, everything that I described in election is not unbounded code. Like, it cannot be unbounded. We always will need to get like the top X nominators to then run the election on top of. Yeah, and this is the last of the current election palettes. If there are no questions, I'll continue with like some bottlenecks that we have. Actually, okay. Yeah. Was there like I heard like a notification or something? Did someone have a comment or no? Okay. So yeah, we have a bunch of snapshots. It's actually, sorry, a bunch of bottlenecks. It's actually better if I explain them in the next slide where I put some visuals of them.
Yeah.
Yeah.
Yeah, I had one comment, but I got to go now, sadly. The questions in the comment is like, why especially the fragment algorithm as compared to other voting? I guess it's pretty complicated to implement.
So why fragment as opposed to any other algorithm?
Yeah, I mean, there are different voting algorithms, so.
Yeah, it's opinion. It's opinion of, I don't know, years ago, Web3 Foundation kind of decided on it. But kind of the protocol is encouraging, or hopefully there will be a time where we encourage some scientists to go and come up with some crazy, deep learning algorithm that beats fragment, and it's great. That's for the benefit of the network. I mean, I know the guys from SR Lab are one of them is quite interested. He always asks me like, okay, how much is the reward now? Like, should I go and do it? So,
okay, cool.
Yeah.
I
No,
will
but
look
the
at the recording later.
Yeah.
Yeah, I got to go now. Yeah, good. Bye-bye.
Bye-bye. So, a few bottlenecks that we have here. The worst one is when we are creating the snapshot, which again is a pretty nasty process, quite controversial as well, because we can avoid making the snapshot, but then it creates its own Pandora box in some ways of issues that I kind of chose that this is the less of the evil. When we're creating the snapshot, we're doing this nasty thing where we're reading a map and we're putting it in a vec, and then we're shoving that vec into a storage value. It's quite what we teach frame devs not to do, but this is like an exception. And then, yeah, there we have like some memory limits there. We also have weight limits there, and this red thing means that this has already broken once, like it already has blown the chain once. So that's one bottleneck. The staking miner is like a time bomb, let's say, like, and by this I mean the size of that transaction that we need to send. And by time, I mean we still have a lot of time until we hit that bottleneck. As I said, I think the solution sizes are now within a few dozens or at most a few hundred kilobytes. So we're quite far from a few megabytes, which is the bottleneck, but yeah, someday it'll come. A little bit more severe is when we're verifying solutions. So we do verifications at some point over this signed queue. Also, whenever we submit, whenever a validator submits a solution, it's verified on the fly as well. And this verification also isn't as memory intense, but it is still quite weight intensive because you're reading, like, you need to go and check all the edges and check all the nominators, blah, blah, blah. So the off-chain worker runs out of memory because remember, these verifications, like this code runs on-chain, but it's rather simple code. This poor off-chain worker is, but this Parity staking miner is doing a shitload of computation, but we don't care about it because it's a binary that lives in a different machine, or it's completely decoupled from the node. But this poor off-chain worker is in WASM, tied to the node, and it needs to like run fragment, run reduce, do all that heavy stuff, and then yeah, this can also very easily run out of memory or just exhaust the node in various different ways, which is why I'm emphasizing that the unsigned submission is really just a backup. We should put all of our eggs in this region. And finally, one bottleneck, which I classify as kind of dangerous, but it hasn't broken yet, so I better keep my better keep an eye on it, is that once the staking is also processing all the results, it's also a lot of data that's in memory at one point. Yeah, currently it's all bounded, won't break, but as we scale the system, this is also another pain point. Anyhow, how we solve this is we basically pagify everything. So everything gets divided into multiple pages, and instead of happening at once, happens over multiple blocks. So, and the assumption for now, at least in the current draft implementation that I have, is that we have multiple pages of voters and just one page of targets. Like we're basically assuming that the number of validator candidates can always fit within one block's worth of memory and weight and stuff. But it's quite easy to then, this could be like a version 2 or 3 improvements to make the validators, aka targets, also pagified. I didn't do it now just to keep the code simpler and smaller. And I love this graph. I mean, this is like so small. I need to probably, okay, is it too small? Okay, no, I think it's readable. So yeah, it's like the same thing, same process, but now this is the new way that things work. So before the signed phase or any signed phase starts, we have this other phase that's called like snapshot creation phase or something like that, where we call into the function that gives us the voters, but then this time we also give it a page index. So we give it, hey, give me the second page of voters. Then we tell it, hey, give me the first page of voters. And then we tell, give me the page 0 of voters. This is an opinion, and these indices are somewhat, let's say, an opinionated decision from my point or from my side, that we always interpret these page indexes as the number that's remaining. So when we tell to the staking palette, hey, give me the second page of voters, other than saying give me the second page, we're also telling it, hey, there's 2 more calls that's coming afterward. Yeah, it helps somehow, but then you have this weird thing where you need to remember that the first page is not 0, it's actually the highest one, or we actually also call it most significant page. So yeah, ignoring all these sides, let's talk a little bit more about this. also, it's important now to keep in mind that, so let's say we have 60,000 voters or nominators, and in each page we can fit 20,000. The first call to like voters page 2 should give me the best ones. This is also why we call it the most significant page. Yeah, and in the first call to voters, or at some point, we also pass on the only page of targets that we have. So anyway, in the span of multiple blocks, we create this snapshot, and it's all dependent on how many pages of voters we have. And this process is powered by pallet staking and pallet backlist working hand in hand, basically. Then the sign phase starts, and then different entities can now submit multiple pages of solutions. So you go and and the way that it works in a little bit more detail that I haven't encoded in this graph is that you go and first register yourself as saying, hey, I have a solution with this score, and I intend to submit it in the upcoming future. That's one transaction. Then there's a separate transaction or separate transactions where you submit each page individually. So this bottleneck that existed here gets also somewhat alleviated. And lastly, no, not lastly, but next in detail is that the solutions do not need to be full. Let's say, I mean, here we have 3 pages of voters, but some solutions might only use 2 of them, let's say. But there is always a, let's say, implicit reference between a page of solution and a page of voters that it's built on top, let's say. Yeah, and this is somehow encoded in the coder. It's somehow implicitly always tied together. So if you have a 3-page solution, it's kind of trivial, but if you have a 2-page solution, actually these lines are kind of wrong here, because if you have a 2-page solution, in reality, you're always using the 2 most significant pages of snapshot. So voters index 2 and voters index 1. But anyway, we have the same system here as well. Eve is malicious, Bob is correct, and Parity staking miner is kind of useless or not doing anything valuable. And then we certainly won't have one block like we had here when we verify this queue. This needs to be its own multiple blocks. So we dedicate multiple blocks, the length of which is variable and an open question, to now let's try and verify stuff. So we start with Eve's first page. It's valid. Like this page, as far as we checked this page, everything that's in it is correct. But the second page that Eve has submitted contains some edge that didn't exist, for example. So this becomes invalid. And the second solution in this case is correct. So then again, each page of these solutions leads to its own partial support, like partial list of backings. Which is again stored as and all of this stuff is stored as double maps, of course, stored in multiple storage, let's say, items. Yeah, and similar to the previous one, any solution that is not checked is discarded, and whoever submitted it gets their money or deposit back. Moving on, the unsigned solutions, for now, again, for the sake of simplicity, will only compete by submitting a single page solution. The reason for that is a little bit beyond the scope of this talk, I would say, or I can get into it if someone asks it. But the main reason is that we cannot verify unsigned solution from validators over multiple blocks. And that basically limits us to just single page. And for now, for the sake of simplicity, the unsigned solutions are only single page. So this is only useful if, for example, all of these miners fail, and then we have at least a single page solution that is representing the top, let's say, 20,000 nominators, and the chain moves on until these multi-page submission miners get their shit together, basically. And then at some point, a call to elect with some page index comes to the election palette, and where we export, when we start the export process of this multi-page solution to staking. So Yeah, there you have like a call to elect with index 0, elect to index 1, elect to page 0. Again, these page indexes are both a page index and implicitly mentioning how many pages are remaining, actually. And then staking will need to process this stuff on its side as well. Like, it needs to merge these different pages into a single page support and eventually convert it to its own data structure. And this is again another time bomb, like a timer thingy here, because this part of the code I have not yet really implemented and cannot be done at the moment, because like this is already such a huge change and refactor that's coming, and it's going to solve, like, it's going to remove this bottleneck, it'll partially solve this, it'll solve this, kind of solve this, but yeah, won't really solve this one yet. And I guess we just have to tackle it one by one. And the reason is that, like, these palettes are all written from scratch and they are designed to work multi-page. Staking, unfortunately, is really designed not like that. And refactoring it is its own beast, so it'll come on at a later point. For now, the assumption is that even if we have a multi-page solution, they need to be such that they can be safely and in a reasonable weight with a reasonable weight consumption processed and aggregated on the staking side. Yeah, some food for thought. This multi-block stuff, especially like multi-block solutions, kind of suck. Or one big hassle of them is that you can only know the score of a solution at the very end. So basically, a 3-page solution has 4 verification steps. Each page needs to be valid based on its local snapshot data and everything. So this is like the 3 pages that need to be valid. And finally, all the 3 pages together, they constitute the score of the solution. That also needs to be valid. So that's like quite a pain. Another concern, or no, not really concern, just a thought, is that how many blocks would you assign to the signed verification? Because you don't know how many blocks you're going to need. You know that in each block you check one of these. So you either check something as correct or you check one page as incorrect. But how many pages do you need? The first one might be invalid, the second one might be invalid, and so on. And you need to make a decision in this range. So if the variable pages is the number of pages that your system has. So in this case, this whole system is 3-paged. You need to choose a number between the range of pages and pages multiplied by the maximum size of that queue, like maximum number of people that can submit. So if you have like 5 people who can submit, and each submission can have 3 pages, you probably want to, or you might want to allocate up to 15 blocks to verify this. Because if all of them are invalid, you need 15 blocks to actually know that. But in the best case, if the first one is valid, you only need pages, so like 3 in this case. One interesting thought is that even though I called this single page submission from the validator as like a backup, in principle, a single page solution can actually eject, like kick out a multi-page solution. I just wanted to emphasize again that it's the score that matters, nothing else. Like, it's not the page size. And lastly, one side effect of the system is that there's a lot of data to be cleaned, even if everything goes well. I mean, if things go wrong, there's even more data to be cleaned. Like, there's a lot of data that needs to be cleaned, especially like this queue. Like, this queue can be massive in terms of like byte size and stuff. And this like kind of sparked an idea for me to do it all like, let's say, asynchronously and later in a garbage collected fashion. So I'm not sure if I would do this, but or maybe it can again be like an upcoming feature. But how I imagine that this would need to be done is that in most cases, the first submission is honest, or it's a good one, or in some cases. And then, but there's going to be more people who submit. And this is like megabytes of data that's stored in storage that needs to be deleted once everything is good. So, and how I would probably do it is that this would all happen, let's say, later on while the election system is on idle, using the, well, idle as in not doing anything, using the unidle hook with like some utility palette to which you give like some storage keys and say like, hey, delete this for me whenever you can, and just tell me when you're done. And we just make sure that by the next day in Polkadot, when the next election wants to happen, that utility palette has done its work. Yeah, I'm generally quite interested in like implementing this kind of like background tasks in Frame, and have made some failed attempts in the past. I might try again here, something like a garbage collector for this palette, for this whole system. And the reason for that is that eventually we want this whole thing to be like a parachain friendly or parachain ready. And for that, it's very critical that we don't like read write a lot of stuff. Although thinking about it again, I think deleting data is not really affecting the size of POV. Maybe someone can correct me now. I think deletion is actually not that expensive. Anyway, but that's just another idea that might come, but currently it's not really implemented. Yeah, and the new way that these palettes are organized is you have the same SP NPoS elections, frame election provider support. And then the new palettes are currently in 4 different palettes. There's a parent palette, palette election provider multi-block, which probably I will rename to something shorter. And it has 3 sub-palettes that do their own thing. These 2 are kind of clear what they're doing. And there's one palette that only does the task of verifying solution and keeping the best one queued. So basically this bit of the work, something like this. So it's a palette that can accept requests to verify stuff, and it always keeps the best one somewhere in storage. And the dependencies currently is that the child palettes, the child palettes, like these guys, can read from the parent palette, but not the other way around. So, and the reason for that is that the parent palette is containing some very, let's say, generic information like phase and snapshots, like the snapshot data. Actually, it's only these 2. This line in the slide is incorrect. The queued solution is kept in the verifier palette. So yeah, the parent palette is actually not doing that much. Like the only logic that it has is rotating the phase, like just keeping an eye on the current block number and making sure that these phases are enacted and notified, which is just one storage item that's changed, and everyone else just listens to changes to that storage item. And yeah, all other communication is done basically via other traits and signaling. But yeah, this whole thing is a good example to look at for like how to do like multi-palette crate or something like that, or nested palettes. I think someone had an idea to do something along those lines. And the palette election provider multi-phase will be deprecated at the end of this migration, at the end of this group of work. And the last slide, what is yet to become. So as I said, my hope with this talk was to make more people like aware of what is the current state of affairs and what's coming. So hopefully more people more people can review it, because that's historically been a huge bottleneck. I think the next step, which I called like milestone -1, because it's not actually doing anything, is that I want to migrate all of the code to be multi-page capable, but actually do everything in one page. So ideally, there would be no logical change, but a lot of functions are going to get that extra argument of page index, because we're assuming there could be multiple pages, but that argument is always going to be 0 because we are the last page and there's going to be no further calls. And then once we have this, it's quite easy to add the rest of it, because the rest of it is just new palettes, and we can just add the new palettes and deploy them, but deploy them in like a dry run fashion where we let the multi-block election do stuff and completely battle test it in production on live chains, but don't really use it in production yet. Like we can keep the old code and deploy the new one next to it and let them both run, but use the old code until we're confident that the new one is good. Yeah, and eventually we switch this, like we delete the old stuff and only use the multi-block stuff, at which point we can scale this system as well. Like we can have basically there would be this one configuration parameter, number of pages that the election system works with. And every time we increase this by 1, the whole system takes more time, but then it can process more nominators, basically. Up until a certain point, of course. Like at some point, we run out of blocks. But in a parachain, that's okay. In a dedicated election parachain, that's not a concern. Or at that point, we have other issues to solve. I think with this, we can hopefully scale to enough nominators for the foreseeable, at least short-term future. But the next important milestone that I referred to, and I have to keep referring to myself, is that this is like a time bomb. At some point, staking needs to be rewritten, probably not from scratch, but significantly to deal with this stuff and just generally become much more multi-block friendly. I think the core problem that we cannot do it right now is that there's somewhere in the glue between the slashing code and staking where we expect staking to know all backers of all validators in one call, like in one go. And if we have multiple pages, then we need to check all of them. And that, I think, is too big of a change, or something in that API breaks, basically. But other than that, it's also like always a tricky operation to change the staking code. So with all of these changes coming, I intentionally didn't apply the minimum changes to staking yet at this point, but it's in my plans to change it as well. And finally, this should be like this solution is deployable on a relay chain, of course. It's pretty suitable, but it's really valuable for a parachain, which is already like on the roadmap of Parity to develop, ideally this year, if not as soon as possible, like a dedicated staking/election parachain or something like that. So yeah, with that, I am done. Thank you for your attention. I hope I have I hope it was comprehensible, at least to some extent. I'm open to questions if anyone has any, or any discussion, actually. I mean, not really questions.
That was great, Kian.
Well,
Thanks.
Yeah. Can you talk more about the issues that we have ran into last year? Namely, I believe the Polkadot chain was breaked or frozen for a while. It was not produced because of something in staking.
Yeah. So the problem there was that so it was a combination of two problems. Like the core of it was staking, but then there was another one on top of it, which made it, I would say, catastrophically worse. So there was a point where I or no one else predicted that we would run into memory issues. So our only bottleneck in how many nominators we accept for the snapshot was weight. And I have done some predictions around that. And I knew that this would reach a limit around 50,000 nominators or so. And I've already like shilled in some places that, yeah, we can support up to 50K or something. And I think if I remember correctly, around 30K, the size of this vector was more than 8 megabytes in memory, which at the time was the limit of our WebAssembly allocator. Of course, we upgraded this, like we bumped this now, so the limit is 16 megabytes actually. But we still, we after this incident, we're being super careful with like the size of VEX in runtime anyway. So yeah, the thing that happened was that the WASM runtime would panic that the allocator is failing to create the next memory chunk or whatever. So the WASM runtime was failing. And then someone, if I'm not mistaken, actually Wei from Parity, he runs validators. He switched to native and produced blocks. But then there was another issue that at that point in time, there happened to be an inconsistency between WASM runtimes and native runtimes because the undeterminism in the code.
Rust behavior of a sort function.
Yeah, exactly. Yeah. So eventually, when the network also started recovering by relying on all validators switching to running native, we had then consensus issues and forks and stuff, which I mean, a lot other people other than me helped solving. But yeah, that was a tough day, let's just say. But yeah, the core of that problem goes back to that snapshot creation, which this thing clearly solves for the most part. Again, my big worry, or something that I have to like constantly remind myself and make sure doesn't happen, is that at the end of this pipeline where we're aggregating this data and this election result stuff in staking, there is a potential for the same thing to happen. But now this time, hopefully we've all learned, I've learned, the code is bounded to begin with. Like all of these vectors in staking will become bounded by the end of this group of work. So hopefully that won't happen, I hope, anymore. But yeah, I think one thing that we're going to see is that, or one thing that I predict we might want to do is, currently we allow oversubscribed nominators, and it would actually help big time if we don't allow, like we just trim them before submission, which we can because miners are opinionated and our Parity miner can be opinionated and just do that. Because the main bottleneck on the other side, on the staking side, is that we have this struct exposures, exposure, which is basically support, as 100% equivalent to support, is one validator's backers. So if one validator happens to have, let's say, 25,000 nominators backing them, there we would get the same error. There we would get the same allocator error. And the thing is, if one validator happens to have 25,000 nominators, it's almost no use because only the top 512 can be rewarded anyway. So other than the fact that the current code bounds that, I think we should just bound it to the number of rewardable nominators, and then, yeah, then this hopefully at least won't happen. But we would still have problems with inclusion of nominators, let's just say. I mean, there would be nominators that maybe won't be included in any solution. Because they are not in the top 256 or 512 backers of all the people that they voted. Does that make sense? Yeah, so you as a nominator, if you vote for example, 16 people, all 16 of them are winners, but you are not in the top 512 of any of those people, you're still not part of the election result, at least. But this is already the case, so we're just making it formal to make sure nothing breaks. But yeah, there's a good postmortem written for that. I think it was around June last year, that day.
Yeah, remember.
Yeah.
So the problem that you mentioned was that the vector was getting too large. That's like over 8 megabytes, and as a result, yeah, correct. So as a result of that, we reinstated the minimum staking requirement, which is originally like 40 dots or something. Right.
So okay, I can talk a little bit more about Sorry left that. What we did after that was like let's say a panic move of bounding the number of nominators A, and then introducing this chill other transaction, and third, introducing the minimum staking requirement. Minimum staking bond that you need. And as a result, what you could do, first of all, that bound, you could never just go beyond that. I think we're actually quite close to reaching that. Let that load so we can check it live. We're kind of close to it, but I will get to the conclusion. This is actually a good point. I should talk about this as well. Yeah, so with the combination of these three features, first of all, the first one is like a safety. We would never go beyond, let's say, 20-something thousand nominators under any condition. And if we are at 20-something thousand, we set this minimum to a value, let's say 40 dots, 60 dots, 80 dots, such that some of the people fall below it, and then this chill other transaction can be used to basically chill them, and then they're not nominator anymore. This is like a manual, this is like doing what the backed list is going to do, but doing it manually. And in the coming release of Polkadot, backed list will be fully enabled. And then we can actually, I wouldn't recommend making it unbounded again, but we can like increase the number of nominators that Polkadot can accept to 100,000 or something. And it's no problem anymore because we can effectively choose the top 20-something whenever we want.
So the question I was originally about to ask was that before there was indeed a time where we tried to have an unbounded number of nominators as well, and which exactly led to this problem because it was unbounded. And before that, we also had a minimum amount of bond at stake. But that if I recall correctly, is more dynamic, and it's like calculated now. And so my question here is: does the minimum bond at stake in these two timelines actually represent the same thing, like trying to solve the same problem?
Almost. So the historical minimum bond was because at the time we only had unsigned submissions, and the unsigned submission was implemented also very ineffectively, or not in a good way. It wasn't weight friendly, and we had to trim the solution such that it would fit in a block. Just the process of submitting it and verifying it would fit in a block. And that was so, let's say, inefficient that it would only support around 7,000. But this process was dynamic because it depended on the weight function of that submission, basically. And what was the other part of your question, or did I answer it already?
The other part was, well, I'm just simply trying to compare because there are two minimum bonds, staking bonds that we had. And I'm just wondering.
So the first one wasn't set by anyone. The first one was set by basically these off-chain workers, these staking miners. Like if I go let's say hypothetically, if the current staking miners that are run right now are all run by me, and if I go and change the code right now to say, hey, anyone that's under 100 dots, don't include them. Is that really a bond? Is that really a minimum? No, I think that's more like just the opinion of whoever is submitting. And the first minimum, the dynamic one, was an opinionated minimum applied by our off-chain worker code. The new one, the current miner also has it, but we don't reach it ever. Because as I said, the current code is much better weight-wise, generally like it's a little bit more better in those aspects. And I think we only have to remove someone from a solution to save weights around 50,000 nominators or so in a single page. So we're never doing it. But the new multi-block stuff has new trimming. We call these trimmings, basically. So the miner that computes the solution can decide to trim it in certain ways to make sure it's included on chain. And that these dynamic limits are all some kind of trimming. And they're all because there's either a length limit or a weight limit, or in the new code, as I said, there's a max backers per winner limit as well, because we want to make sure it doesn't break in the end in the staking size, in the staking side. But these are dynamic. And also, like a good miner, if it wants to trim something, would go and sort and trim from the bottom or something like that. But a random miner might just, do random shit. So there's no, these are not hard limits. They're completely dynamic. It's quite a challenge communicating this to the external people, to external nominators. I mean, we're doing like this monthly updates now, and I think if someone reads all of that and spends like some time contemplating on it, would follow. But we actually try and explain this stuff with Zeke in these updates. But I totally understand, like, this is quite bad for the end user. Also, the bags list is quite complicated for the end user. Like, it's very soon we have to go, especially to the Polkadot nominator community, and tell them, hey, you have to go and click this button every now and then, and maybe it helps you get a reward, but maybe it doesn't. It's not very optimal yet, but we'll get to it. I mean, it wasn't a priority yet. It's just like other stuff to solve. But
yeah, so the reason why I'm asking all these questions is because it gives me and gives everyone a sort of context and understanding the sort of optimizations that you are planning to make in the upcoming roadmaps. And yeah, I'm just trying to figure out like what exactly is it about here, how the kind of issues that we ran in the past, and why you're basically to limit the number of nominated voters or nominators in the snapshot, and so on and so forth.
Yeah, No, these are great questions. I mean, in answering them, I come up with good, or it's very valuable to answer them, because you usually come up with good ideas. Let's also talk about the snapshot. So all of this, not all of this, most of this is because of the snapshot. And let me also talk about why we could actually live without the snapshot as well. So without the snapshot, as I said, there are two benefits to the snapshot. First, it allows us to index or refer to voters, nominators, and validators in a smaller way, but there are other ways for that as well. There are literally on-chain indices, and we can incentivize people, indices that actually, as far as I know, not that many people use, and they're smaller, right? I mean, someone can correct me if I'm wrong, but they are literally a small index, like and definitely less than 32 bytes. I mean, whatever they are. We can incentivize validators and nominators to maybe set an index or have an index, and then we can use that as the smaller representation. That partially solves the size problem. But then the other situation is that if you don't take the snapshot of the staking data and freeze it in some way, then staking itself needs to be frozen. And the code used to be like that at some point, and that was also quite nasty. So 2 hours a day, Polkadot staking was basically like, we close the door now, like you can come back in 2 hours and submit your nomination or something like that, because the anything that affects the election result cannot change while someone is trying to compute it, because otherwise, someone removes a vote and suddenly a solution becomes invalid. That would be chaotic. So yeah, there was some thoughts or some discussion I had with Wei at some point. He was a big fan of like not taking a snapshot. I eventually wasn't convinced, or I don't know, we just decided to do it this way for now. But that's still an option, or still, I don't know, something that I'm happy to be debated about. But I think it's better this way still. It's less of the evil. But yes, because you mentioned why are we limiting the number of nominators?